Okay, let's unpack this. You ever hear an idea that just sounds, well, completely absurd?
Oh, definitely.
But then you stop and think, maybe 100 years ago, someone saying you could call across the Atlantic instantly. That would have sounded just as crazy, right?
Exactly. It reminds me of that Einstein quote. Something about ideas needing to sound absurd at first.
That's the one. If at first an idea does not sound absurd, then there is no hope for it. It really makes you wonder about all the impossible stuff in science fiction today.
And what's really interesting is how that line, the line between possible and impossible, keeps shifting, doesn't it?
It totally does. As we learn more, things change.
New discoveries pop up, and suddenly ideas that were pure sci-fi start looking, well, maybe not so far-fetched anymore.
Yeah. And, to really get our heads around this, we've been looking into Michio Kaku's book, Physics of the Impossible.
Ah, Kaku. He does a great job explaining complex ideas.
He really does. And what I found super helpful was how he breaks down these impossibilities. He has three classes.
Right, the classifications.
Yeah, class I is stuff that might actually be doable. Maybe not tomorrow, but, in the foreseeable future.
Stuff that doesn't break any known physics, just needs better engineering, basically.
Exactly. Then class two, that's the really long-term stuff. Maybe possible in like thousands of years, assuming we figure out a lot more physics and engineering.
Pushing the boundaries of known science, but still theoretically possible within those laws.
And then there's class three, the real head scratchers, things that seem to just smash right into the laws of physics as we understand them today.
Yeah, those are the ones that would require a complete rewrite of our fundamental understanding.
So think of this as like your shortcut to some of these really mind-bending concepts.
This is a useful framework, isn't it?
Yeah.
Helps us sort of map out the landscape of future possibilities
Hmm.
and think about where science might be heading.
Definitely. So our mission today is basically to dive into some of the coolest ideas from the book, give you the rundown, the key insights. Where should we start? How about force fields?
Ah, yes. The classic sci-fi staple. The shimmering, invisible, wall-stopping laser beam.
You've all seen it.
But the actual idea of a field, this real physics. Think about Faraday and magnetism.
Right, his lines of force.
Exactly. He pictured these invisible lines reaching out from magnets, affecting things. And it's funny, because he wasn't great at math, supposedly.
Really?
Yeah, so he had to come up with these visual models, and they were so good, we still use them to teach physics today. It's quite something.
Huh. Okay, so how does that connect to, like, a real force field? Akaku talks about a classic possibility, plasma windows.
Yes. That's a fascinating real-world example.
Yeah.
Happened back in 1995, I believe. Brookhaven National Lab.
So what is a plasma window?
Well, imagine heating a gas up so incredibly hot that the electrons get stripped off the atoms. That's plasma. It's this super energetic charged state of matter.
Okay.
And because it's charged, you can use magnetic fields, which, interact with charged stuff to kind of contain it, shape it.
Ah, like a magnetic bottle?
Sort of, yeah. And they created this contained sheet of plasma that was transparent, but it acted as a barrier. It could separate, say, a vacuum from normal air pressure.
Wow. So like a window on a spaceship that actually holds back space.
That's the kind of potential application, yeah.
Okay.
It's a real physical barrier made of energy and contained plasma. Pretty amazing stuff.
Okay, that's class one. What about class two? Magnetic levitation comes up.
Right. We see that with superconductors. The Meissner effect, where a magnet just floats.
Yeah, that's cool. Needs to be super cold though, right?
Typically, yes. That's the big hurdle for superconductors. Getting them to work at room temperature would be revolutionary for things like maglev trains, power transmission, and maybe even force fields.
But Kaku also mentioned levitating frogs with just magnets.
It did. And it's not superconductors. It turns out water and frogs are mostly water, right?
Yeah.
Is diamagnetic.
Diamagnetic meaning?
Meaning it very weakly repels magnetic fields. Normally you don't notice it, But if you have an incredibly powerful magnet, like seriously powerful,
You can push the frog up.
you can. The repulsion is enough to counteract gravity. It just floats there. It shows how powerful magnetic fields can be, even interacting with seemingly non-magnetic stuff like water.
That's wild. Okay, still in class two metamaterials. These sound like something straight out of a lab in a movie.
They kind of are. This is where things get really interesting for invisibility too, but for force fields.
Hmm.
Well, think about bending energy.
So, researchers at Duke Imperial College, they made materials that could bend microwaves.
Exactly. Materials engineered at a tiny scale, smaller than the wavelength of the microwaves themselves. They have a negative refractive index.
Negative refractive index. What does that mean in simple terms?
Normally, light or microwaves bend a certain way when they enter a material, like water or glass. These metamaterials make them bend the opposite way. So you could, theoretically, steer waves around an object.
Making it invisible to those waves.
Precisely. And later, Caltech and others started doing similar things with visible light, using something called plasmonics.
Okay, so could that create a force field, bending energy away?
Potentially, for certain types of energy, like light or microwaves. But a true force field, stopping physical objects or powerful energy blasts? That's harder. And bending all colors of light at once, practically. That's a huge challenge for these materials. We're not talking Harry Potter's cloak yet.
Right, flexibility and working across the whole spectrum.
Yeah, it's often a clunky setup for just one specific frequency right now.
What about holographic projections? Kaku mentions that for invisibility, but could it simulate a shield?
Invisibility maybe by projecting a fake image of what's behind you, but as a shield, probably not. The technical hurdles for creating a convincing real-time 3D hologram are immense anyway. The data processing alone.
Okay, so that leads us to class three, the real deal. The Star Trek shield's deflecting phasers.
Yeah, Kaku suggests that would likely require manipulating the fundamental forces of nature themselves, like gravity or the strong and weak nuclear forces.
Stuff we barely understand how to control.
Exactly. Maybe some combination of things, a plasma window layer, maybe some kind of laser curtain, super strong carbon nanotubes. You could simulate some aspects. But a single field that just repels everything, that seems to violate known physics.
So interacting with the fundamental forces, that's the barrier.
That appears to be the major conceptual barrier, yes. How do you generate and control a field that interacts so strongly and selectively with incoming energy or matter? We just don't have a mechanism for that in our current physics toolkit.
All right, let's switch gears. Another classic, invisibility.
Ah, yes. The power to be unseen. It's a fantasy that goes way back. Greek myths, H.G. Wells.
Gosh, Gordon, Harry Potter, it's everywhere.
It taps into something deep, I think. The desire to observe without consequence, maybe?
Could be. But technically, Kaku points out we already have a form of invisibility, right? Stealth tech.
That's a good point. Stealth bombers, fighters. They aren't truly invisible to the eye, but they're designed to be very hard to detect with radar.
How does that work again? Is it the paint?
It's partly the materials. Yeah, radar absorbent stuff. But it's also the shape. Maxwell's equations, which describe electromagnetism, tell us how radar waves reflect. So stealth planes have all those weird flat angles specifically designed to scatter radar waves away from the source instead of reflecting them straight back.
Making it look like nothing's there on the radar screen. Clever.
Very clever application of physics, yes.
Oh, but for actual visual invisibility, we're back to those metamaterials again, aren't we?
We are. That seems to be the most promising scientific avenue right now. The ability to engineer materials that literally bend light around an object.
So the light from behind the object just flows around it and continues on as if it passed straight through.
That's the principle, yes. If you can control the refractive index perfectly at every point, you could guide the light seamlessly around a hidden volume.
But the challenges you mentioned before still apply, making it work for all colors, making it flexible.
Absolutely. Huge challenges. You need nanotechnology to arrange atoms with incredible precision, and getting that negative refraction to work across the entire visible spectrum simultaneously. That's the big one. We're still a long way from a practical, wearable invisibility cloak.
Kaku also touches on holographic invisibility and even using a fourth dimension. Those sound even further out there.
Extremely speculative, yes. Holograms have the data problem we discussed, and manipulating extraspatial dimensions. Well, that's deep into theoretical physics territory. Class 3, most likely.
Okay. Firepower time. Phasers and Death Stars. Handheld ray guns are everywhere in sci-fi. Any basis in reality.
Well, in Class 1, Kaku talks about lasers. We have lasers, obviously. Powerful ones.
Yeah, industrial cutting lasers, surgical lasers.
Exactly. Gas lasers, chemical lasers, solid-state lasers. The basic technology for creating a focused beam of energy exists.
So what's stopping us from having a phaser pistol?
Mainly size and power source. To get a beam powerful enough to be a useful weapon, you currently need quite a bit of equipment and a hefty power supply. Not exactly pocket-sized.
But Kaku thinks maybe nanotechnology could shrink things down. Better battery.
That's the potential path forward, yes. Miniaturization is key. If you could make highly efficient, powerful lasers and pack a lot of energy into a small battery or capacitor, maybe some kind of directed energy sidearm isn't completely out of the question down the line.
Yeah.
Still a classy stretch, maybe, but conceivable.
Okay, but what about the Death Star? Blowing up planets with a giant laser. That's a different scale.
A vastly different scale. The energy required is just mind-boggling. Kaku explores where you might even get that much energy.
Like fusion, harnessing the power of the sun.
Fusion is one theoretical possibility. We're working on controlled fusion power here on Earth, trying to fuse hydrogen isotopes. It's incredibly difficult to contain the superhot plasma stably and get more energy out than you put in. Scaling that up to planet-destroying levels, monumental doesn't even begin to cover it.
What about those nuclear-pumped X-ray lasers? Teller's idea.
Ugh. Project Excalibur, that era. The idea was to use the energy from a hydrogen bomb explosion to pump a laser medium, creating an incredibly intense, short burst of X-rays.
So the bomb is the power source.
Essentially, yes. Hugely powerful in theory, but also, well, you're detonating nuclear bombs, and aiming it precisely is another massive challenge. Very much a theoretical weapon concept with enormous difficulties.
And then he mentions gamma ray boosters. Natural space lasers.
Those are the most powerful explosions we know of in the universe, releasing focused jets of gamma rays. They are, in effect, cosmic lasers of unimaginable power. But harnessing one, aiming it,
That sounds like class 3 for sure. Maybe class 3 if there was one.
definitely feels like something only a super advanced Kardashev Type 3 civilization might even contemplate, trying to manipulate stellar scale objects like that.
Okay, so handheld ray guns, maybe a distant class 1. Aiming stars, definitely class 3. Got it. Last one, teleportation.
Beam me up, Scotty.
The ultimate shortcut. Instant travel. It's even in, like, ancient texts, isn't it? Religious stories.
There are accounts, yeah. Philip in the Bible, for instance, supposedly transported supernaturally. It's an old, old dream.
But classical physics, Newton's physics, just says no, right? Stuff is solid, it has to move through space.
Correct. In the classical view, objects occupy a specific location and have to travel through all the points in between to get somewhere else. Matter can't just dematerialize and rematerialize,
But then quantum mechanics came along and messed everything up.
as it tends to do. Quantum theory introduced really strange ideas, like particles being probability waves, not just little balls, and the idea of quantum leaps.
Where an electron can jump from one energy level to another without existing in between.
Sort of, yes. It's more about the probability of finding it changing instantaneously. And this leads to even weirder stuff, like quantum entanglement.
Ah, Einstein's spooky action at a distance. Two particles linked no matter how far apart.
Exactly. If you measure a property of one, you instantly know the corresponding property of the other, faster than light could travel between them. It's bizarre,
But didn't Einstein have a problem with that? The EPR paradox?
He did. He thought it implied faster than light communication, which relativity forbids. But it turns out, while the correlation is instant, you can't actually use entanglement to send meaningful information faster than light. It's a subtle but crucial distinction.
Okay, but we have achieved quantum teleportation, right? Kaku mentions teleporting photons, even atoms.
Yes, but it's important to understand what's being teleported. It's not the particle itself dematerializing and rematerializing. It's the quantum state, the information describing the particle that gets transferred.
How does that work?
It uses entanglement. You entangle a pair of particles, send one to the destination, then you interact the particle you wanted to teleport with the entangled particle you kept. This destroys the original particle state, but allows you, using classical communication like a phone call limited by light speed, to tell the person at the destination how to manipulate their entangled particle to perfectly recreate the original's quantum state.
So you're teleporting the information, essentially destroying the original to recreate it elsewhere.
Precisely. And they've done this with photons and even the collective state of atoms in things called Bose-Einstein condensates.
BECs, those are the super cold atoms that act like one giant superatom.
That's right. Cooled to near absolute zero, thousands or millions of atoms lose their individual identities and behave as a single quantum entity. Scientists have teleported the quantum state of these condensates. The big challenge there is keeping things that incredibly cold.
Okay, so teleporting information, teleporting the state of a few atoms. That's real. Class I, maybe. But beaming up Captain Kirk?
Ah, that's the class 3 impossibility. The sheer amount of information is staggering. You'd need to scan the exact quantum state of every single atom in the human body, trillions upon trillions of them.
And transmit that information perfectly and then reconstruct it atom by atom at the other end.
Exactly. The data storage, transmission, and reconstruction challenges are astronomical, not to mention the energy required. And as Kaku notes, sci-fi like Stephen King's The Jaunt often explores the horrifying things that could go wrong if the mind arrives before the body or if the process isn't perfect.
Yeah, maybe some things are best left to science fiction.
For the time being, at least.
So, wow. We've gone from force fields to invisibility, phasers to teleportation. It's been quite a journey through Kaku's classes of the impossible.
It really highlights the spectrum, doesn't it? Some things are maybe closer than we think, while others, well, they challenge the very foundations of physics.
What really stands out is just how much our definition of impossible relies on our current understanding. History is full of examples, right? Atomic bombs, going to the moon, things that were considered utterly impossible not that long ago.
Absolutely. Scientific breakthroughs can completely reshape that landscape. What seems like a class 3 impossibility today might, with some fundamental new discovery, shift categories entirely. We just don't know what we don't know yet.
It leaves you wondering. So, a final thought for you listening. Of all these seemingly impossible things, force fields, invisibility, teleportation, ray guns, which one captures your imagination the most? And what kind of breakthrough do you think it would take to make it real? Something to ponder, definitely.